So our next invited speaker is Dr. Sanjay Choudhary. Sanjay is currently a postdoctoral research associate working with Professor Robert Kelly in the Department of Materials Science and Engineering at the University of Virginia. Originally from Raipur, India, he earned his master's degree in materials science and engineering from the Indian Institute of Technology in Kanpur in 2016. He then worked as a corrosion scientist for TA Steel India Limited for 2 years. In 2022, Sanjay completed his PhD at Monash University in Australia, where his work was recognized with the prestigious 2023 Morris Cohen Award by the Electrochemical Society. Congratulations. His current research focuses on passivity breakdown and localized corrosion in metallic materials and developing electrochemical methods for studying corrosion mechanisms at the nanomicron scale. Sanjay, I apologize for everything I mispronounced in that bio there. Please forgive me. But please, the reins are all yours. We look forward to your talk and thank you so much for being here.
Thanks, Jen. You can hear me, right?
Yes, sir. We can see your screen perfectly.
Yeah, thank you. So again, thank you so much for the kind introduction, and thanks to your protochips team and CMAS and Ohio State University for organizing these, and then also giving me the opportunity to present my work here. So before talking about the work, I would like to thank my supervisor, Professor Kelly, for his invaluable support and guidance. Our TM manager, Dr. Helga Henrik, again, protochips team. Dr. Winkler from NC State. I also used the facilities at NC State. All of them for helping and advising for the experiments, and the DARPA for funding the work which I'm going to present today. So let me start with why we needed Liquid-Cell TEM. Here at UVA, I'm trying to study localized corrosion in aerospace grade aluminum alloys, which basically get their strength from nanoscale features like dispersoids and nano-sized metastable and stable precipitates. However, our understanding in regards to their contribution to the passivity is limited. We do believe that the fundamental understanding of corrosion mechanism at nanoscale would be crucial in developing appropriate corrosion mitigation strategies and developing next generation materials for emerging technologies. This is an ongoing work, but if interested, you can check the following article where I used ex-situ TEM analysis, but the work would definitely highlight the importance or the need of in-situ TEM to study this complex phenomenon. Now, that was just one example, but in corrosion science, we have several fundamental questions which need the eyes of electron microscopy. Corrosion electrochemistry that involves oxidation of the material, and the electron being generated from the oxidation gets consumed in reduction of electrolytic species. Now, depending on the material, electrolyte, or applied potential, the oxidation process or the mechanism could differ. But when it comes to nanoscale phenomenon, for example, the selective elemental dissolution or onset of passivity or passivity breakdown, all of these for the mechanism proposed to date need experimental validation, and that is where in-situ TEM comes into the picture. So how do we do corrosion studies in Liquid-Cell TEM? So this product, it is already introduced by Jenna and even the previous speaker. So the most important part is this top chip, which has 3 electrodes, all made of platinum. Working electrode is printed on the silicon nitride window. If you're interested in corrosion studies, one can deposit a thin film of material of interest on the window connecting the working electrode, or deposit a material as nanoparticles on the platinum electrode, or get a fib lamella of area of interest and weld it onto the electrode, of course by exposing the electrolyte, or you can also polarize the specimen and study the phenomenon happening at specific potentials. So here are a couple of examples using in-situ TEM for corrosion studies. This is one of the earliest papers which I could find using basically studying pit nucleation in aluminum, but again, of course, they used aluminum thin film, and they captured pit nucleation when they exposed it to 0.01 molar sodium chloride. Here, what you see is selective dissolution of matrix phase from magnesium, zinc, calcium alloy. It was only exposed to DI water. But probably one of the best example is from Delft University, which actually highlighted the immense potential of liquid cell TEM for our corrosion community. So what we are seeing here is selective dissolution of magnesium and aluminum from S phase, followed by redistribution of copper, enriched copper. This is a complex phenomenon, and the TM is the only way to see such something like that. And this reflects a continuous evolution of electrochemical properties of these nanoparticles or the submicron particles during microgalvanic corrosion of 2000 series aluminum alloy. The work from University of Manchester showing selective dissolution of manganese sulfide inclusion from stainless steel when exposed to DI water, and which is basically known to act as a nucleation site for localized corrosion in critical stainless steel structures. But one thing which is common in all this example is that they are happening at a free corrosion potential, and depending on material, the process could take much longer time, much longer to be able to see something in reasonable experimental time. So the polarization is something which helps in accelerating the oxidation process so that one can capture phenomenon in quicker time. And then also there are many electrochemical processes which happen, so which occurs at certain potential. So the polarization, that is where helps. So here is one work from our group. It is a similar same material as the previous example. Stainless steel, we have manganese sulfide inclusions, and during anodic polarization you could see the dissolution of the sulfide. So, and you could see the process within 10 minutes, which was not the case in previous example, which took almost 24 hours to see something something without polarization. But what you don't see here is that the electrochemical response what we are getting here is not just from stainless steel lift out. We also have the platinum working electrode exposed. So in fact, without external applied potential, the stainless steel has already been polarized anodically due to being contact with platinum, and this is called galvanic corrosion, and that is not what we want to study. So galvanic exposure has always been the question when we talk about corrosion studies in liquid cell TEM. So to avoid the galvanic contact or exposure of galvanic contact, we do have a few solutions. So one which we use at UVA is something called TOS deposition in FIB. So after welding the specimen, one can deposit a silicon oxide layer insulating the entire platinum. This is the work. The second one, this is the work from Delft again. So Ali Kosari and his team, they had fully covered the platinum working electrode with silicon nitride, and they removed only a specific area, just enough to weld a fib lamella, and then covered the joint again with TOs. So these are the ways to cover the platinum electrode so that we don't have the galvanic issue, or the response is only coming from the sample. Now that solves the galvanic issue, but platinum being a reference electrode could be a problem for many studies. For electrochemistry, what we need is a reference electrode whose potential does not change with time or during polarization or changing electrolyte. And that is what we get with our commercial reference electrodes. The one of the image shows one of the commercial reference electrode, AgCl reference electrode, but you could see that is much bigger in size relative to the TEM holder. So it is almost impossible to insert this big reference electrode for inside the TEM holder. So to solve this, so I guess I think we can also talk about the limitation of platinum in this sense that there is no interfacial interfacial equilibrium, and that is why the potential is not fixed. And then if it is polarizable, if you change the electrolyte, its potential will again change, and that is why we do not have any thermodynamic scale with respect to platinum as a reference electrode. So to solve this issue, we worked with protochips, and we proposed the concept of metal bridge. So let me explain what is metal bridge. So here what you see is a conventional 3-electrode setup, and platinum is a working electrode. We have ferric ferrous solution as our electrolyte. We get a beautiful CV, and using our commercial reference electrode. If we use platinum as a reference electrode instead of using a true reference electrode, there is a significant shift in the potential scale, and that is what you see here. But what we realized is that instead of using platinum as your reference electrode, if you use it as a bridge and have a true reference electrode in a different beaker, that gives identical result as the conventional setup. So yes, it was an interesting work for us, and we also explored the applicability of metal bridge in different aspects of electrochemistry, and then also the limitations as well. So it turns out there is no effect of scan rate. You get exactly similar result as the conventional setup. It turns out there is no effect of the length of the wire or how much wire is exposed in either side. It turns out you can use any metal wire as your metal bridge, and you can also use it for conventional corrosion electrochemistry test, like potential dynamic polarization or electrochemical impedance spectroscopy. So how does it work? To understand that, we need to understand something called bipolar electrochemistry. So here's a 2-electrode setup, and we are flowing a current between them. If you measure the potential difference, you get a potential difference, like this. But what is going to happen if we put a metal plate in between, which is not electrically connected to the circuit, but it separates the cell into 2 different cells? And will the electrochemistry go smoothly with this? It turns out that current still flows through the cell, and without being electrically connected, the metal plate in between gets polarized, and the surface facing anode becomes cathode, and surface facing cathode becomes anode. And in this case, the potential what you're going to measure will be the 2 cells potentials. And if we rearrange this equation, what we are getting is this additional term, which is nothing but the potential difference between 2 ends of this plate. And the offset, if you compare it with the conventional setup, this offset actually depends on how much current you are flowing through this circuit, and of course the electrolyte in each side. If you have the same electrolyte and if the current is negligible, your offset is also negligible. Both surfaces are at their corrosion potential or open circuit potential. And that is what we have in our setup, because we are putting a metal wire in between reference electrode and working electrode where there is no current flow, or at least it is really negligible. So the two ends of this wire, yeah, they are at their corrosion potential, and that is why the offset is 0. And this is the reason behind your result showing that we get exactly same potential as our conventional setup, provided that the electrolyte in both the beakers are same. So, so our suggestion for metal bridge setup, when running electrochemical test in Liquid-Cell TEM was like this. So this is a conventional setup where the cable coming from the platinum reference electrode we used to connect it directly. But now one can use that as metal bridge and have a true reference electrode outside the holder or outside the TM. And based on this, we have the prototypes has this external reference electrode kit, and then having the Faraday cage gives much more stability and then also reduces noise in the electrochemistry data. So with the metal bridge setup, definitely we solved the electrochemical measurement related issue. But we had another issue with fib lift out. As you can see, when corrosion progresses, the specimen gets crumbled, making it difficult to focus one specific side. And for this, so there were some other suggestions from the community that it is better to have relatively thicker lamella. Of course, that would limit the resolution of any features you want to see. But that definitely helps in avoiding this kind of incident. And then also we can coat the lamella from the both side or the place which is not of interest, and then see the corrosion progresses from only one edge of interest. And this is what Ali Kosari did when he wanted to get the information regarding this complex phenomena happening in S phase. Now, the preparation and the placement of fib lamella on each chip is also important, and the people preparing fib lamella would definitely agree with that when you prepare a bigger sample, or even in normal sample, there's a possibility of bending. And if our sample doesn't look nice like this, and if it is bent, then you have issues with focusing the entire sample. And also during assembly, it is possible that forces from the bottom chip window might lead to the damaging the sample, or you will lose the sample. So yeah, so there is a little bit of experience you need to get the lift out over the A chip. Now, when we talk about fib lamella, there has always been this discussion on the effect of gallium implantation or gallium contamination when we prepare the lift out specimen. Although electrochemistry wise, we do not have any result or any work showing the effect of gallium implantation. Basically, we still need more work to understand that. But if you are worried about gallium issue, one can get a lift out specimen from an electropolished sample and then weld it onto the E-chip, and you could see two work from, again, University of Manchester. Now let me talk about one of the most asked question in Liquid-Cell TEM, I guess, the effect of electron beam. There's no doubt that electron beam has effects, and depending on the electrolyte, it can change the composition, and that would again affect the electrochemical data. if you have, the electrolyte, like copper sulfate, or the cases where the electrodeposition can also happen, you will see the consumption of copper, soluble copper into because of formation of nanoparticles, and that is why your liquid composition is also changing. So yes, if not careful with dose rate, there's also a possibility that you might damage the feature of interest. So yes, each user will tell that they would have seen something showing the effect of electron beam in their experiment. But there is no quantitative measure of radiolysis effect yet, which can be subtracted or which can be used to talk about this data. But there has been some finite element modeling predictions for just water radiolysis. Here what you can see is a finite element prediction, of course, showing if you use neutral to alkaline electrolyte, increasing the dose rate would decrease the pH. And this graph showing if you increase the flow rate, the accumulation of those radiolytic species would decrease. So this can also give us a critical flow rate to avoid accumulation of all those radiolytic species. But these studies use kinetic parameters obtained from bulk experiments to predict changes in thin electrolyte setup. And that is not the right approach if you think about it, because as you can see that the limiting current we get in liquid cell TEM is much smaller than what we get in bulk experiment. So we performed cyclic voltammetry at different scan rate in bulk as well as in liquid cell setup, and then the relationship between peak current density and scan rate can give us the effective diffusivity. And it turns out for this specific setup, the diffusivity of the ferric ferrous species is almost 73% of the bulk diffusivity. And this geometry factor would change if there's a bulging. So there is still more work to do, but the electrochemistry can definitely help in many aspects, including quantifying the effect of radiolysis, because the K term also includes the concentration. So if someone can repeat the same experiment with and without electron beam, and will have a change in this parameter. Now, hydrogen bubble. Sure, hydrogen bubble is problem for many of the experiments because you dewet the cell. But it is really interesting that many researchers, even the previous presenter, also using that as advantage, and you can get a really good imaging condition because now you replaced the electrolyte with the bubble. And this is what you see in this work, where researchers from Cornell, they have two different conditions. One where they generated the bubble and they could get a really good image, and the second case where they are flowing the hydrogen gas in fully dewetting the cell and could get a really atomic resolution. But this approach is good for this kind of experiment. It doesn't, at least we have not been successful with our foil experiment. And when you generate bubble, it is possible that you might destroy the foil, and that is what you see here. But without a doubt, I think the controlling the hydrogen bubble generation as well as removal would be a really interesting stuff. And then the high flow chip of proto chips, that is going to be really important. Not just for this, and even for other energy studies as well. And when it comes to controlled generation of hydrogen bubble, we think the metal bridge would be really important, as we have the thermodynamic scale for hydrogen bubble formation. And if you know where exactly you're polarizing and when does hydrogen gas forms, that would be the key to explore these kind of questions. Now, one last slide. The metal bridge has been a really interesting work for us, and definitely that comes from the problems which we had with the Liquid-Cell TEM. So Liquid-Cell TEM is also helping us explore the unexplored aspects of electrochemistry, and now one can use metal bridge in the places where you need a really small reference electrode, or wherever you needed a leakless reference electrode. You don't want a mixing in electrolyte, and wherever previously you were using a pseudo reference electrode like platinum or other metal wire, you can make them as a metal bridge. I also used the metal bridge setup to study electrochemistry in a droplet. But again, as I said, the cases like fuel cell or batteries, we can use metal bridge to get the potential with respect to true reference electrode, which is not possible previously. So let me quickly summarize it. Whatever I was discussing today. So yes, TEO's coating can be used to avoid galvanic contact. But what we have realized is that there is still more work to do on that regard as well, in optimizing the deposition parameter for better insulation. And then also use of TEOs is also limited for a specific electrolyte, because it is silicon oxide, which might not be stable in alkaline pH. So I'm sure there are other coatings options to solve that issue. Worried about gallium contamination, of course, electropolished specimen is the way, but again, we need more work to see the effect of gallium. If the gallium effect is not much, then the lift out specimens also would work perfectly. Now, cell geometry and electron beam definitely have significant impact on electrochemistry, and we need to quantify those effects to relate the findings to bulk scale behavior, without a doubt. And then hydrogen bubble, of course, the hydrogen bubble would be an interesting chapter of Liquid-Cell TEM. We could see that imaging, we can get a better imaging, but I see much more and very interesting work with that. And then for all these things, metal bridge could be of use, confirming if the TEOs has fully covered the platinum, or you want a controlled hydrogen generation. Effect of anything on the electrochemistry, metal bridge could be of use. And then again, as I said, it is not limited to only in-situ TEM, can be used for any restricted geometry or small volume of electrolyte. So thank you so much for listening. I've put my email here as well. Anyway, I would love to have your questions, but if interested in getting contact with me, feel free to send me an email.
Wonderful. Thank you so much, Sanjay. Really appreciate it. What a great talk. I know there's a lot of interest surrounding corrosion, and then of course Ohio State University in particular has, in addition to UVA, right, some of the top experts in corrosion as well. So between the two of you, your universities, and the techniques that are available there could be some really interesting in situ corrosion work done.
Indeed, yeah.
Yeah, so we got a few questions for you, and if anybody has any questions for Sanjay, now's a great time to put it in the chat. And we are running early, which is great. And so Vita, if you're ready in the next few minutes, we can go ahead and move on to your presentation as well. But let's go ahead and take a look through the questions. So the first one I have here is, thank you so much for the presentation. How long is a typical corrosion experiment when everything is going well? Like how long are you in the TEM, it sounds like maybe?
I think that is a good question. And to be honest, I do not have an exact number because, depending on the sample preparation, which is, I think, to be honest, which is what the key time-consuming step is, preparing a few lamella and then putting onto the e-chip. But again, I take that one as one day, and then for electrochemical experiment, the next day is fully booked for that. But I do think that with much more experience, probably I can decrease that time as well. But for now, the entire corrosion process, I take it 2 days.
Yeah, that's pretty good. Fib preparation in general and deposition onto MEMS devices can be very nuanced. And so, yeah, we've tried to help with some guides and stuff too, but ultimately you kind of have to figure out your sample and what works best for it.
Yes.
Next question I have here is, did you find that flow rate helped prevent beam damage in your electrolyte?
So that is a great question. Actually, we use electrolyte like sodium chloride, where, to be honest, we do not have, at least I would say that we don't see much of effect there. Of course, there will be pH changes or something, but we have not realized much changes in the electrochemistry data. So I think, to be honest, like there's more work to do in regards to the flow of species within the cell. To date, we haven't, even without flow, we haven't seen much effect. So I guess we were not using high dose rate.
Okay, that's good. That's good for you. And then this last question right here, and you may have touched a little bit on it at the end, but maybe there's some elaboration. The TEOS coating, the TEOS coating, what's the material that is going down, and does it have any effect with your electrolyte?
So it is silicon oxide, which gets deposited, and then you have a volatile gas which is getting evaporated. So silicon oxide, we are considering that as like insulating or non-conducting things. So I would definitely assume that there will be some loose particles which will flow when we start electrochemistry, but I guess I do not have the answer to that if there is any kind of dissolution which is also like contaminating the electrolyte. But that is a good question. We did not think about that in our previous experiment, but I think that would be a topic to explore for sure.
Yeah, it keeps you busy, right? There's always something to explore. No, that's great. Well, thank you. That covers the questions that were submitted so far. And again, if anybody thinks of a question for Sanjay, you can go ahead and put it in the questions box, maybe with his name next to it. And we'll have some time at the end to cover any additional questions that may come up. Sanjay, thank you so much for always an amazing talk. Thank you very much.
Thanks.